Hello, and this is the third video in the Thermodynamics series. We're talking about Hess's Law now. Again, Hess's Law is just another way to calculate the change in heat energy, or the heat that goes into or out of the system during a reaction. So this is what we've been doing with all of these calculations, all of these thermodynamic formulas, where it's all trying to figure out the same answer. It's just when you have different pieces of information, you have to use a different formula. But all of these are trying to figure out the change in energy, either the energy that is absorbed by the substance during the reaction or the energy that's given off by the substance during the reaction. And this Hess's law is used when you have two similar reactions. They're called component reactions. Two similar reactions of the same substances of the reaction in question, the reaction we're trying to investigate. So when we have two other reactions using the same substances to compare this reaction to, then we can calculate the change in energy of the reaction we're trying to investigate. So when you calculate the energy going into the system or out of the system, we're calculating the change in the heat energy, and that's called enthalpy. This is what we've been doing this entire time, is calculating the enthalpy of these reactions. So delta H, or the amount of change in heat energy, or enthalpy, as it's known, it's all the same thing. Enthalpy, that's what this enthalpy means. Now this Hess's law is used, as I said, when you have the energy changes of two component reactions of the reaction in question. Now component reactions, more specifically, they're reactions involving the same substance as the reaction that you're investigating. But the two component reactions will algebraically combine to form that original reaction that you're looking into. And you'll see what I mean when we get to an example. So here is an example. You find the enthalpy value of the reaction. So we have P4O6 plus 2 oxygens yields P4O10. And see, we don't know what the enthalpy is for this one. So this is the one that we're investigating. This is the reaction we're investigating. Now here are the two component reactions, and you'll be given this on the test if you need to use Hess's law to find out the enthalpy change of this original reaction. You're going to be given on the test these component reactions, so you'll know that this is a question that you'll need to use Hess's law to solve. So as you can see, these two component reactions have the same substances, they're just rearranged. So P4 plus 3 oxygens yield P4O6, and the energy change for this, or the enthalpy, is negative 1640.1 kilojoules. And then the second one is P4 plus 5 oxygens yields P4O10. And that enthalpy is negative 2940.1 kilojoules. And what you're going to want to do is you're going to want to rearrange these two component reactions in such a way that when you combine them together, when you cancel out all of the like terms on either side of the yield arrows, and you combine them together, you want to get this original formula. So you'll see how to rearrange that, how to rearrange these component reactions here. So it's like a puzzle game. When you want to read, here's the original reaction that we're studying, that we're investigating, and you know this is the one we need to find the answer for, because this is the one we don't have the heat energy for, or the enthalpy for. So that means these two are the component reactions because we have the enthalpy for both of these. Now, what I mean by rearrange is that you take one component reaction at a time, either this one or this one, and the first thing you want to do is you can reverse one of them. So we're going to reverse this yield arrow right here and make it go backwards. And then whatever you do to a component reaction, you have to do to its enthalpy value. So since we reversed this one, the enthalpy value, this negative 1640.1, you change that to a positive. And if it were already a positive, then you would change it to a negative. And that's all you have to do for that if you reverse this component reaction. And then after you reverse the component reaction, you combine these two component reactions to see if you get the answer or the reaction that we're studying, that we're investigating. Now here are the rules to the puzzle game. You can only rearrange one component reaction at a time. You can rearrange the component reactions as many times as it takes, but just do one at a time. Like, don't reverse both of them. Just reverse one of them and see if that fixes things. Don't reverse both of them and then try to combine them. Or you can multiply one of the component reactions by a number, and if you say if you can multiply everything in a component reaction by the number 2, so that you would multiply its molar coefficients by 2. So if we did that, that's not the answer for this, but just for an example, if we did that, we would end up with 2p4. And this 3O2 would turn into a 6O2 because we're multiplying by 2. And you got to multiply everything across the reaction by 2. You got to do whatever you do on one side of the yield arrow, you have to do on the other side of the yield arrow. So if you multiply the molar coefficients on one side of the yield arrow by 2, then you also have to multiply the molar coefficient on the other side of the yield arrow by 2. Now let's try this example. As I said, that was just an example of how to rearrange things, but that wasn't the answer. Let's try this example. The reaction in question is this P4O6 plus 2 oxygens yields P4O10, and we know this is the reaction we're trying to get to because it doesn't have, that's the one that we need to find out the enthalpy change for. So down here are the two component reactions. What we do first is the first thing you want to reverse one of these component reactions. So I'm going to reverse this top one. And if you reverse a component reaction, remember you have to reverse the enthalpy of that component reaction. So we're going to reverse that and we're going to change this to a positive 1640.1. So let's rewrite this down here underneath in its reversed form. So that would be P4O6 yields P4 plus 3 oxygens. And then the new enthalpy of this reaction would be positive 1640.1. All right, now, and that's kilojoules, obviously. So now we have this component reaction reversed, so we can cross off the component reaction we used up. We used that one up already, so we reversed it. So we'll cross that one out. So now we have left the one leftover component reaction and the new component reaction. So let's combine these and see if they result in getting this formula up here. So let's look at this for a minute. Let me change colors. And here it is written all nice and pretty so we can look at it easier. So let's look at this for a minute. Here's the first component reaction up here is this P4. Now, if you look on the other side of the yield sign on the second reaction, the second component reaction, there's a P4 over here. So what do like terms do when they're on the opposite sides of equal sign or a yield arrow in an algebraic equation? They cancel each other out. So we're going to cancel this P4 out, and we're going to cancel this P4 out. Now let's go on to the 5 oxygens right over here. 5 oxygens, and let's look on the other side of this yield arrow on the second component, the other component reaction. Now that has 3 oxygens. Now as long as they're both molecular oxygen with the O2, not just plain old O, as long as they're O2, we can cancel these out. We can cancel 3 of them out. Do you see how there's 5 O2s up here and 3 O2s down here? So this 3 O2, 3 oxygens will cancel out completely. And this 5, we took 3 of them away. So now this 5 O2 is just a 2 O2, is just 2 oxygens. Do you see that? We canceled out this 3 O2 completely, took away the 3 oxygens. So whatever we did down here we have to do up here. So we took away the 3 oxygens from these 5 oxygens, leaving 2 oxygens. And then this P4O10, it doesn't have anything. This is different than the P4O6. And so these stay. Now let's rewrite these 2 equations now that we've canceled them out and combine them and see if we get this reaction equation up here. So P4O6, so let's rewrite the P4O6. That's from the second component reaction. And then yield arrow. And then, oh no, I'm sorry, not the yield arrow. P4O6. And then we need to include the 2 oxygens, the 2 oxygens from up there. So P4O6 plus 2 oxygens. And then the yield arrow. And then what we have left over after these other was canceled out is the P4O10. So let's write the P4O10 down here. Now let's compare this new formula with the original formula in question. P4O6 plus 2 oxygens yields P4O10. Is that the same thing? Yes, it is. So we don't have to do anything else with these component reactions. Now, what the next step that we do is we take these component reactions enthalpies and we add them together. And see, you have to take the new enthalpy that's been changed to a positive in order to get the correct equation. So positive 1640.1 plus negative 2940.1 is negative 1300. And negative 1300 what? Negative 1300 kilojoules. So your answer to what the heat enthalpy or the enthalpy is for that original equation is negative 1300 kilojoules.